Welcome. On Thursday I mentioned the zero-point energy problem briefly, and I wanted to add a comment about this. It's an interesting problem in physics. If you read about it, Wikipedia article is good, and also a couple of books. I consulted a book of Milton about the Casimir effect. It's an interesting question what the vacuum is, and there are, mathematicians, physicists, philosophers thinking about that problem. The vacuum is not empty, there are virtual particles everywhere, and they fill out space and somehow produce energetic ground state, which one would like to understand. How big is it? And so one can measure the attractions of two conducting plates, and it's an attractive force which is 1/a⁴, and strangely enough, if you take spheres, according to this book here of Milton, if you take spheres, then it's actually a repulsive force. So it's not so quite obvious what you actually do here. And it's related to the cosmological constant problem. Some even think that there is no cosmological constant problem because the discrepancies are so severe. 120 orders of magnitudes are reported discrepancy between what one would expect the zero-point energy to be and what one measures from cosmological measurements, large-scale measurements. So it's an interesting problem. I'm not a physicist, so I don't know much about it, but it's just for me a vexing, interesting question. As a mathematician, I'm interested in problems which I can tackle. So the mathematician can look at simpler problems. Let's look at the bounded operator and look at the lowest spectral value. That is then called the zero-point energy. In the case of, here's an example, if you take the lattice, a one-dimensional lattice, you can take higher dimensional lattice. This is completely understood. You can look at the Fourier transform. Instead of L2, little L2z, you can look at L2z, where it's a multiplication operator, and then you have the spectrum is a equilibrium measure on the interval 0, 4. It's kind of one of the Julia set cases, one of the trivial Julia set cases. This is the density of states. Everything is explicit, but you can also look at the graph. Can be infinite, can be, for example, this, and you can then look at the Hodge Laplacian on this graph, or on the Chirikov Laplacian if you want, any kind of a reasonable Laplacian which is locally defined, and then you can look at the smallest eigenvalue, which is in the graph case or simplicial complex case always given by 0. So this is L is equal to d squared, so the spectrum is never negative, and the 0 eigenvalues lead to cohomology, and so in the case when the graph is contractible and connected, then there is only one ground state, one vector of length 1, which we would call this the vacuum. So 0 here maybe is the most natural thing to call. In this case, example 1, 0 is the vacuum solution. It's not an element in the Hilbert space here, so there is no eigenvalue, right? So this is continuous spectrum. Now there is a big machinery here. What do you do when you add a potential, like the almost Mathieu, or random potential, or whatever you want to look at, and then you can look at the spectral problems. Also interesting are nonlinear problems, and that's how I started, to get into mathematics. I was looking at the standard map, this Frenkel-Kontorova model from 1938. Jakov, Frenkel, and Tatiana Kontorova have looked at this problem of solving such a nonlinear system of equations. It's an interesting problem, and if you write it, you can write, this is a second order difference equation, you can write it as a first order difference equation for a vector, and that's the standard map which can be written as a map on the torus, which is probably the most famous problem in chaos theory, is to study this and show that for c bigger than, large enough for c bigger than 2, you have some positive entropy. I worked on this for more than 10 years, and it's a very interesting problem, but it's also related to a nonlinear equation which you can look at. You can look at special solution, almost periodic solution or periodic solution, depending on whether alpha is rational with respect to 2 pi or irrational. So you get here a problem, a nonlinear equation for a smooth function, and it was Morser who proved first the twist theorem, telling stability in the sense that qx equal to x has a solution close by for small c. That's the KM theorem. In higher dimensions, this doesn't lead to stability. There is this Arnold diffusion. It's an interesting problem what happens here in general on a higher dimensional lattice. So one of the difficulties is the vacuum. Zero is just at the boundary of the spectrum, so it's not invertible. You cannot use the implicit function theorem to continue this solution qx equal to x for positive c. So when you take the derivative and you linearize the problem, then you get kind of an almost Mathieu type operator, but it's not sinus of n alpha, but it's a sinus of qn alpha, which is a deformation of the almost Mathieu. So soft implicit function theorems don't work. One needs hard implicit function theorems like the Nash-Moser-Newton iteration. So you apply, you take the linearization, but you kind of invert it on a class where you can invert it, like alpha is Diophantine, so that you can do that, and then you regularize. So it's very technical, and Moser first did it for 333 derivatives. This later has been pushed down by Hermann. Now, I was just mesmerized when I looked at such Laplacians that changed the Laplacian type. Here, this Laplacian, which is defined by the Dirac matrix, by the exterior derivative, is not invertible, and it's based on inclusion, right? When you take the derivative, you look at smaller dimensional simplices. Here, there is an operator which is using the intersection and not the inclusion. And what happens, so this is the definition, you take the dxy entry is just 1 if x intersecting with y is 0 and 0 else. Generalize this. It's quite a general framework. You can energize that. I wrote about this for several articles. And what is important to see that G doesn't have to be a finite graph or finite simplicity complex. It can be a lattice. It can be Z. It can be higher dimensions. It can be any dimension. So the only thing which we need for that theorem here is that it's locally finite, meaning that the unit spheres, have some uniform bound on their size. So that's what I write here. Locally finite doesn't have to be uniform. A lattice, it can be, that triangularization of a manifold. But just what we want, we don't want the unit spheres to become, larger and larger and larger. So there should be a bound on the size of the unit sphere, which we have the number of simplices which are connected to another simplex. So this uses language from topology, finite topology of Alexandrov. And the very nice thing, that's how I got into this topological thing, is that you can explicitly give the green function. Now, if you look at this story here from physicists when they tackle that, Milton, for example, is a physicist who works on electrodynamics, wrote textbooks on electrodynamics. It's a heavy subject, and green functions play an important role. Green functions are just inverses of Laplacians, higher than Laplacians on forms also. And so the green function, just the inverse, is explicitly given as the Euler characteristic of the intersection of the stars, or ux and uy. So because of that and the local assumption here, this is a bounded operator. And this is a bounded operator here, so, and that's extremely nice, right? We have actually a gap which is uniform. The only thing which matters is how large these spheres get. So if you make a bound on this, you can estimate how big this gap is until something interesting happens. And one of the consequences is if you look at this Frenkel-Kontorova model or any nonlinear perturbation here, then u equal to 0, something you want to have u equal to 0 to be a solution on the right hand side. Any such problem here, as for small c, you can estimate how big the c can be, only u equal to 0 as a solution. So in some sense, the vacuum u equal to 0 is stable. So that's very nice, and that's what I wanted to say today.